Okay, polar covalent bonds. We've talked about covalent bonds. You explored covalent bonds in a previous activity. We're going to talk about what makes a bond polar. All right, so what makes a bond polar, and then we're going to see why a water molecule is polar, and also why water dissolves some ionic compounds. It doesn't dissolve all ionic compounds, but the method by which it does for some of them I'm going to show you, so you can better understand Lab 8. What makes a bond polar? This is an example here of a nonpolar covalent bond. A nonpolar covalent bond exists between two atoms that are sharing electrons equally. We know a covalent bond is formed by two atoms sharing their electrons to obtain a stable octet by the Octet Rule. The Octet Rule tells us that an atom likes to be stable by having the same electron configuration, which means it's isolated electronic, for a noble gas. Right? So atoms that are close to the noble gas helium will be satisfied with 2 electrons, while everyone else, all the other atoms, are satisfied when they have 8 valence electrons. And this is true whether you bond with ionic compounds or you bond with covalent bonds. So this is an example of nonpolar. Now polar, you can think of as something as having 2 ends, or something is different on 2 sides, kind of like the poles of the Earth. You have a north and a south pole. So if we look at a polar bond, which is this case right here, notice that we have hydrogen and we have chlorine bonded to each other. We know that's a covalent bond because these are 2 nonmetals. Two nonmetals create covalent bonds, and they share their electrons. If we look at the Lewis dot diagram, we can see exactly where all the electrons are. Hydrogen is happy because it's got 2 electrons, these 2 shared electrons. Hydrogen has, and it's happy, it's stable. Chlorine's also happy because it has 8 valence electrons. One of these shared electrons came from the hydrogen, and one of these came from the chlorine atom. But they're not sharing them equally. These electrons, as you can see, I've made them a little bit closer to the chlorine to represent what's happening. Why are they pulled closer to the chlorine? The simple reason is that chlorine has an electronegativity that is larger. It's 3.2. Well, hydrogen has electronegativity that's only 2.2. We find these values on table S of the reference tables. Now you might say, how do they know what the values are for these? How did they come up with these electronegativity values for the atoms? Well, what they did is they bonded atoms together, and then they looked at the electrons between them and saw which way they went. And then they ranked each atom based on how much its nucleus pulled those electrons toward it. So really for us, we're looking at numbers that were determined experimentally by scientists so that we could find out if something is polar. This is a polar bond because the electrons are not shared equally and they go toward the chlorine. It makes that chlorine a little more negative and it makes the hydrogen a little more positive because electrons are negative. So how can we tell if a bond is polar, a covalent bond is polar? We look at the electronegativity difference. So first, a bond is nonpolar if the electronegativity difference between the atoms in the bond is 0 to 0.4. So here are some examples. If we look at a bond between hydrogen and hydrogen, which does happen, in fact, hydrogen doesn't exist by itself as one atom. It always bonds with another hydrogen atom in a sample of hydrogen. And the electrons that are shared between the two of them are shared equally because their electronegativity difference is 0 because obviously each of them has 2.2 for electronegativity from table S. And if we took the difference between them, there is no difference, so it's 0. And likewise, if we looked at if hydrogen and carbon were to bond together, their electronegativity difference is 0.4. And that's also a non-polar bond. And you can see it goes from 0 to 0.4. That includes 0.4. If the electronegativity difference is between 0.4 and 1.7, then this is going to be a polar bond. So if hydrogen were to bond to oxygen in a covalent bond, they're sharing the electrons, they would not share them equally. The electrons are pulled more toward the oxygen because it has that higher electronegativity. And notice that the difference between these two is 1.2, which is between 0.4 and 1.7. And then finally, if we were to look at the difference above 1.7, that's going to be an ionic bond. And we can tell that here because we've got a metal and a nonmetal. That's the other way we can tell. If you recall from the ionic bond presentation, there's two ways we can tell if there's an ionic bond. It's either that the electronegativity difference is greater than 1.7 or that it's made of a metal and a nonmetal. Now we're going to go and see why is a water molecule polar. We know the bonds inside the water molecule are polar, but why is the molecule polar? And we're going to look at this in a lot more detail later on. But a water molecule looks like this. We've got two hydrogen atoms bonded to an oxygen atom. And we know that these shared electrons in the water molecule are not shared equally. They go more toward the oxygen because, again, oxygen has a higher electronegativity than hydrogen does. And their difference is higher than 0.4. So it's a polar bond. Those electrons move up toward that oxygen and away from the hydrogen. And so we represent that part of the region where oxygen is as slightly negative. And the reason it's slightly negative is because the electrons, the shared electrons, are pulled more toward that oxygen because of the higher electronegativity that oxygen has. We represent that with this little symbol. It's a delta negative, and the delta negative tells us that region is slightly negative. It's not fully negative like an ion is because the electrons have not been completely transferred from one atom to another. They're only moved closer to that atom. Because they're moved closer to that atom, that means that they're moved away from another atom, and that atom would be hydrogen, and the hydrogen atom is slightly positive. That proton in the center of the hydrogen atom is now exposed because the electrons are pulled away from it. So it's sticking out from the molecule a little bit and making that end positive. Because you've got a negative end and a positive end to a water molecule, it can do some interesting things. I think they're interesting. And that is, it can dissolve some ionic compounds. Not all ionic compounds, but some. So let's see how this would work. So this could be like sodium chloride, for example. I didn't label it that because I'm just telling you about a general ionic compound. All right, so we've got this sample of ionic compound that's solid. It's got some positive ions in it and some negative ions in it. And they're stuck in a lattice structure, a crystal structure, right? Now, you know when you put salt into water, it starts to dissolve and it disappears, right? That's basically the ions are breaking up into individual ions. And why do they do that? Well, the reason is this. We have this water molecule, and we have millions of water molecules coming up to the sample, the solid sample of ionic compound. And the positive ends of the water molecules, as seen here, come up and they start to tug on the negative ion. And they're pulling on it. And there's millions of them, and they're all surrounding that ion, and their combined strength is strong enough to pull that ion away from the positive ions. And eventually what will happen, it pulls it away, and it is surrounded by the positive end of the water molecules. And that's isolated. And that particle is so small that you can't see it. And that's why when you dissolve an ionic compound in water, it seems to disappear. Also, the negative end of the water molecules will attract and pull away positive ions. And I have isolated one positive ion over here. And so the water molecules are working together to pull apart the positive and the negative ions. So you'll see that in your Lab 8. And that's all I got for you.